start with Rahul's talk on the relationship between complexity theory and obfuscation. And Rahul is an amazing speaker, so I really look forward to this.
That is high praise from an amazing speaker. I hope to live up to it. Yeah, so I'll be talking about this work. It's a joint work with Alex Lombardi. And yeah, I guess by trade am a complexity theorist, and Alex is by trade a cryptographer. And hopefully I'll tell you a little bit about some ways in which these two things interplay with each other. Okay, so what are we going to talk about? So on today's...
You need to know what this is.
I was thinking about it.
I call it a modern TV.
So we'll start off on today's episode pretty easy, pretty easy. What is I/O? And then we'll move into some more background, some Scooby-Doo. Go through it quickly. I'm sure everyone's familiar. Then we're going to move on to Nikon's great-grandfather. And we'll close with 3 different columns, okay? So that's what we're going to do today. Any questions about the outline? Or,
No commercials?
Yeah, this talk is sponsored by BetterHelp. Oh, I should be careful. It's recorded. All right. Okay, good. So that's today's episode. So we're halfway into the first day, so I thought it might be a good time to ask, what is I/O? Yeah, okay. So we've heard a lot today. What do you guys think? Anybody have, what is I/O? If you had 2 words to say what is I/O. What'd you say?
Infinitely often.
Infinitely often. Good. We'll see that. That's great. That's great. Any other contenders?
Input, output.
Input, okay. All right. This is careful. I forget. Cryptographers always think adversarially, right? Like, you have to be careful.
So there was once a Dutch school of sort of theory and practice, and they separated people by exactly what I/O means.
That's good. All right, so as you all said, I/O is a mathematical definition, introduced by Barak et al. Actually, it's kind of cute. Right after they introduced this definition, they had this nice sentence. Some very slight hope that this definition is achievable comes from. It's like if it exists if P equals NP, which I thought was a nice sentence. Starting with like the Sahai Waters paper, there's this perspective of I/O as a central hub in cryptography. And there's some really crazy person out there who thinks I/O is Hakuna Matata. That person is me, but not in this talk. In this talk, we're going to think of I/O differently. In fact, I want you to think about I/O as a wheelbarrow, okay? This is what we're going to be building towards. I/O as a wheelbarrow, okay? Hopefully it'll make sense on today's episode. And in particular, when I was thinking about what the goal of this talk would be, I realized it was pretty much this meme. So here we have a masked, this is Scooby-Doo, by the way. Here we have a masked bandit, I guess someone who's hiding a bit, so that's cryptography, of course. And then here we have a very human-like wheelbarrow, so that's I/O. And I want to argue, or at least in some cases, that I/O kind of makes cryptography into complexity theory. And, okay, what even is the difference between cryptography and complexity theory? Whatever. But at least I think this work, at least for me, really convinced me that in a lot of cases, you can use I/O to reduce questions on cryptography to questions that look more like classical complexity theory. So that's what I'm going to try and argue about in this talk. And really the goal of this talk is to illustrate this phenomena, okay? Like, I don't know about you guys, but I'm like, it's really hard for me to remember things from talks. So like, I really try, like if I'm lucky, if like I'm a week later, I like remember a couple sentences. So like, this is the sentence I want you to remember, if you do remember, okay? And what is not the goal, I'm gonna apologize in advance. We have, if you look at the paper, a lot of results. I'm not even gonna talk about, I'm not even gonna talk about all of them. I'm not gonna go into detail. I really just wanna illustrate this one phenomena So I'm actually going to talk about maybe our simplest result, because I think it illustrates it the best. I'm not going to go too much into some definitions. I'm actually not even going to talk about maybe our most technically interesting thing. I just want to illustrate this phenomena, okay? So that's my goal. All right, so let's get started. And I think, as we've already mentioned in the talks today, one, I think, really interesting phenomena is the unreasonable effectiveness of I/O. And really, I mean the unreasonable effectiveness of like I/O plus P not equal to NP, right? So you have, here's a very small list. There's a much bigger list that Rachel gave in her talk. But you have all these different objects, which are like one-way functions, public key encryption, functional encryption, non-interactive zero knowledge, and they're all implied by I/O plus P not equal to NP. Okay, really, this is... Oh yeah, this is the parentheses around P not equal. Yeah, it's not I/O plus P is not equal to that. Yeah. That would be a really deep statement. If you could figure out what that means, that would be really interesting. And okay, really, this is not P not equal to NP. This is like NP is not NP poly infinitely often. But okay. So there's this phenomenon which is kind of the unreasonable effectiveness of I/O. And I think maybe to first order, we think of like I/O plus P not equal to NP as kind of solving cryptography. It seems like once you have these two things, you can do almost anything you want. If you want to build some object, these two things are really powerful. And so you might think, okay, we can do pretty much everything we want to if we take these two things. And I want to argue that there are at least a few things that are missing from the picture that would be good to get a better handle on. In fact, I'm going to give you 3 examples, and then I'm going to mention very briefly a few more examples, but these are going to be the examples. In fact, in this talk, we're really going to only focus on the first example, but I want to give you a few examples. All right, so the first example is about optimally secure cryptographic primitives, right? So usually when we talk about one-way functions, you talk about security against polynomial time adversaries, or maybe if you're talking about really strong adversaries, you might talk about like sub-exponential time adversaries. But you could ask for more. In particular, you could ask for objects that are secure up to naive attacks. And in particular, intriguingly, while our theoretical constructions usually don't have this property, practical constructions are kind of tailor-made. Like they really want them to have this property, that they're secure up to naive attacks. Like I guess in our paper we cite this other paper that says AES has like 126.1 bits of security or something. That's like the best known as of 2011 or something like that. And
it doesn't have any mathematical meaning, right?
Yeah, sure. Oh, but put that to the side. But yeah. Okay, but this will have mathematical meaning. In particular, we're going to be interested in like time probability trade-offs. What do I mean by that? Let's take an example. Example is going to be one-way function families. The families part is going to be important in a second because of that guy. Okay, so if you have a one-way function, what's the naive attack? I mean, oh, come on, you guys have to be like... Yeah, exactly, great. So the naive attack is just try random points, right? So in particular, if you have t time, you're going to have success probability like roughly t divided by 2 to the n. Because there's going to be 2 to the n possible things it could be, and if you have t time, then maybe you have t tries, something like this. So when I talk about optimally secure one-way function families, what I want a one-way function family that like meets these bounds, maybe up to like small polynomial loss. Okay? Does anybody see a potential problem with this if I like remove this thing here? Do you see any problem with this? Oh, okay. All right. So it is true that there are these like Hellman-Fiat-Nauer style attacks that work for like fixed one-way functions. So if I like pick a specific one-way function for each input length, then you have an attack. We'll talk about families of one-way functions, or you can think of them as like keyed one-way functions. And all of these primitives we can think about as keyed versions. Okay? All right, so what I wanted to say was okay, here is some object that hopefully you would agree would be good to have a theoretical understanding of, and that at least from I/O plus P not equal to NP, it's not clear how to construct this. In fact, this seems like a really non-standard kind of thing, because it's like usually when we talk about LWE or factoring or something like that, there are like non-trivial attacks already. Like it does seem, yeah. Sayan?
The fixed one-way function attacks, I assume like using some non-mutable.
Oh yeah, good. Yeah. So there, the original papers are like there's some data structures, like if you do pre-processing, but there is actually some work with me and GNOME and some other people about like circuits. Yeah. Okay, great. Does this make sense? Okay, great. So that's one example of something missing. I want to give you another example. And this other example is about one-way product functions, right? So this is like a variant of the one-way function question. One-way function, I ask you, here is an output, find me a preimage, right? In the one-way product function case, you could ask, okay, let's say I give you k outputs. I want you to find preimages for all of them simultaneously. How hard is this? So naively, what would you expect? Naively, you'd expect maybe like if you had in that much time like a p chance of doing it, when you have k instances, you might have like a p to the k chance of doing it. So you would expect this kind of direct product phenomena. And so like in the extreme regime, where like you only have a polynomial amount of time and like the one-way function is really hard, you'd expect maybe probability 2 to the minus nk, right? So this is like a really natural problem natural property you'd want out of a one-way function, that it has like direct product hardness. But it's something that we have a really hard time analyzing. And in fact, there are barriers. There are like this like folklore result by Rudich, which shows that like there's black box arguments can't argue for this. And there are even counterexamples where there are things that are one-way functions. They're hard if you want to invert one thing. If you want to invert k things, they actually don't get any harder. So here's like a natural property that it's difficult to analyze, and it actually has some pretty nice applications that I'm not going to tell you about because that would distract from my story. But it's like, yeah. Okay, so here's another pretty natural question that you'd probably want to understand if you want to build crypto that seems like it's missing from our picture. Okay, I want to give you one more example. Last example is about quantum. Let's say you want to get a non-interactive proof of quantumness, right? So one thing that we do have is in the decision tree model in query complexity, we have unconditional separations between classical and quantum. They are problems that take exponential number of queries to solve classically, but require only polynomial number of queries to solve quantumly. So there's like a very natural strategy if you wanted to take that and turn that into a proof of quantumness. Just take the black box result, pretend that I/O is virtual black box obfuscation, and say, hey, here is a way to separate classical and quantum stuff. And okay, if none of that made sense to you, that's fine. I'm not actually going to talk about this very much, but there's like a very natural way to use I/O in order to get proof of quantumness, and we don't know how to do it. Okay? So here's 3 examples of things that we don't really have a good theoretical grasp on how to do, even if you have I/O. Okay? And there are more examples of this that like come up in the paper. I just don't want to spend too much time explaining what these things are, but they're like high-end primitives like lossy and extremely lossy functions, correlation intractable functions, and even actually like mini-crypt objects like collision-resistant hash functions we don't know how to get from purely I/O plus p not equal to NP. So like while like I/O plus p not equal to NP gives you so much stuff, there is a lot missing. Okay? All right. Now I'm going to talk a bit about our results, but is there any questions about like the stuff that I've discussed so far? All right, great.
So just to clarify,
yeah, sure.
These goals are easy if we take, say, ideal obfuscation and one-way functions?
So like, okay, the quantum example is ideal obfuscation is true for. The other 2 examples, it's not clear. If you have ideal obfuscation, like how do you build optimally secure PRFs? Like, it seems like you would need an optimally secure PRF to start with, like, but it is true in the random oracle model. So the first 2 things, if you had a perfect random oracle, then you get them. The last thing, if you have an ideal obfuscation, then you would get it. Yeah. Okay. So I want to talk about our results at a very high level, and this is going to be an extremely high level. Later on in the talk, I'll give a more concrete explanation. But really, all our theorems have the following flavor. You take a wheelbarrow. This is a really strong wheelbarrow. It's sub-exponentially secure. You add in a brick, and you get a house. Okay? And it turns out, like all of these things that I've like mentioned previously that have been missing, you can build all of these houses if you have the right materials. Okay? And I won't tell you what the materials are now. I'm gonna tell you about them as we go, but it will depend on the object. But they're gonna be various complexity assumptions. Yeah.
So your notions of optimality going to extend to like the quantum setting, like say like the best.
Alex, I think that is that true or?
For one-way functions, it does. For the
Oh,
other
right.
stuff, it like does halfway, and we can talk about it offline.
Yeah. Okay, good. So basically, wheelbarrow plus brick equals house, okay? This is a great theorem, not only a nice theorem flavor, but I think in Berkeley, where there's a housing crisis, it's an important construction paradigm to keep in mind. In fact, I encourage you all to be, oh shoot, I was supposed to say, when I said I'm not gonna talk about detailed results, I'm gonna focus in on what'll be useful for illustrating this paradigm. I'm going to focus on like optimal one-way functions. So this is kind of like the easiest theorem, and so I'm going to tell you about this next. But anyway, back to the housing crisis. I encourage you all to be YIMBYs. Who knows what YIMBY is? Yeah, so just shout it out.
Yes, in my backyard.
No, almost close. Yes, IO makes. I didn't. Yeah. If you made a pie chart about how much time I spent on this talk and how much time I spent just on trying to make this work, it'd be like slicing a pizza in half. Yeah, okay, open question. If you can figure out how to make this work, I'd be very interested. Good. All right, so this is our result. Oh, that's good. That's a good point. I should have done that. Yeah. Okay. So this is what our results are going to look like. Now I'm going to tell you a little bit about what the techniques look like. Again, it's going to be at a high level. Okay. So what is our approach? Our approach is going to be as following. We want to show that some crypto primitive exists, right? This crypto primitive could be, for example, one-way product functions. It could be optimal one-way functions, whatever, right? And the approach is going to have two steps. The first step is we're going to use I/O, okay? We're going to use I/O to show that some problem, pi sub q, remember q is our primitive, is worst case hard, okay? In particular, in most of our examples, we're using I/O as a kind of worst case to average case reduction. We want to show that if some primitive exists, if some very related problem is worst case hard. So it turns out that for one-way product functions, like the corresponding pi sub q looks like what we call like k-fold search unique sat. For now, ignore what the unique part is, but it's basically very natural. Like if you have one-way product functions, you ask, can I invert k things simultaneously? For k-fold sat, you ask, here, I give you k sat instances. Can you solve them simultaneously? And in most of our examples, when you go from like the primitive q to like the pi sub q, it's actually really natural what the pi sub q is. Like for lossy functions, for example, it's like the pi sub q is really just determining if you have a circuit that's injective or has a small range. Or for correlation and tractability, it's like related to finding correlation and tractability. It's like actually like these problems, pi sub q, are really, it's kind of surprisingly natural, I would say. Okay, so that's the first part of the approach. So the first part of the approach is use I/O as a worst case to average case reduction. Now we have a worst case problem. So we can hope to use complexity theory to reduce that to ideally some sort of standard complexity assumption. Okay? And like, so in this case, we get something that looks like NP not equal to co-NP for this example. All right, so that's what the approach is going to look like. And I do want to mention, we already have kind of existing examples of this. They're not quite via like this two-step approach, but like there is this result by Komogortsky et al. That says there exists one-way functions if sat is not in P. And in fact, basically combining this with the high waters, you get like all of those examples that we saw before, is that like all of these crypto primitives, one-way functions, PKE, public key encryption, non-interactive zero knowledge, functional encryption, they all reduce via I/O to the hardness of sat, okay? And I think this raises kind of some interesting questions, right? Like looking at this list, I don't know, does it raise any interesting questions for you? What would you say if you looked at this list? What's like a natural question that pops into your head, research-wise?
Exponentially hard.
Great, okay, great. Nice, all right, that's one. Anybody have another? Sorry, someone was saying something.
Where does it stop? And what's equivalence? How do they make it pure?
You said like the hardest image is that is equivalent?
Yeah, okay, yeah, good question. You're asking like, like how far down can you go, right? Good. Okay, so 3 questions that I put on the slide. The first one is, anyone, who knows who this is? Yeah, nice. This is Dick Carp, who I think has like a nice little exhibit outside there. And I call this like the Dick Carp question just because it's like related to some his work in complexity theory. It's like, okay, you could take this, you take that earlier slide, which was like the unreasonable effectiveness of I/O, right? You could ask, why is it the case that like I/O plus P not equal to NP gives me all of these crypto things? It's kind of magical, right? But if you take this perspective that like for most crypto primitives Q, there's a natural pi sub Q associated with it, then it's actually pretty reasonable that for many crypto primitives, you get SAT out. Why? Because it's like maybe the unreasonable effectiveness of I/O plus P not equal to NP is actually just the unreasonable effectiveness of NP completeness, right? Which of course, why is that true? I don't know, but once Dick Carp found it, that was great for us. So I think that I don't have like a technical question associated with this, but it seems like a kind of interesting phenomenon to explore. The other thing which you've all pointed out is, okay, who knows who these 2 people are? Come on, Russell. Okay, this is yeah, good. Russell and Pittori, who I believe were the people who first came up with the exponential time hypothesis, and so this leads to this natural question. Okay, let's say instead of saying that SAT's not in P, let's up the ante, right? What if SAT requires brute force time? Now do we get optimal one-way functions? Okay, and you could ask questions like that. And the last thing I think is pretty natural to ask is like, okay, we have all these primitives, and it's kind of related to your question. We have all these primitives which correspond to SAT. Can we come up with primitives that correspond to other problems? Like, what does this landscape look like? Okay, good. Now I'm going to have a little interlude, but is there any questions so far? Okay, so who knows who this guy is? That's a good guess, not Gauss. Good, good, who said that? Nice, Leibniz. Did someone say carp? But okay, it's Leibniz, but it's also something else. I'll give you a hint. I mentioned it earlier in the talk. What did you say?
Wheelbarrow.
Wheelbarrow. Okay, but along the right lines. This is actually Nikon's great-great-great-great-great-great-grandfather. So if you trace the family tree, there's Blum, under which is Shafi, under which is Nikon. Yeah, Nikon, you didn't make the slide. But I guess for most people in this room, this is your great-great-grandfather, okay? And like any family history, or any family, there is some controversy. This connection, Klein to story, is controversial. Like some sources have it, some sources don't. Some sources talk about other sources having it. I don't know what the story is there. But okay, what is Leibniz famous for? You guys probably know him for co-inventing calculus, but he actually did some stuff in physics. I don't know, does anybody know what he did in physics? He was the guy, this is also somewhat controversial, but like, according to some people, he's the first person to talk about conservation of energy. So like, maybe he's the first person to write down 1/2 mv squared for kinetic energy, and so on. And there's this nice quote, which I guess was burned into my head in high school, that energy is not created nor destroyed, only transferred. And for whatever reason, I like this quote. And to me, this is where like the wheelbarrow comes in. Because to me, I don't know, I'm getting this feeling, I'm not saying this is definitely what is happening all the time, but I'm getting this feeling that like when you're using I/O, it's like you're kind of transferring hardness, right? It's like I/O is not in some sense creating hardness, but it's like transferring it, and it kind of aligns with like some things, like for example, if P equals NP, then I/O exists, but it doesn't let you build any crypto. So it's true, you have this wheelbarrow, but you have no hardness to like transfer. And then as soon as you get P not equal to NP, all of a sudden now you have this one brick and you can build some stuff with it. Yeah, I don't know. I mean, that's just philosophy. So, but I kind of like this perspective. That's why I like I/O as a wheelbarrow. Okay. So now I want to illustrate this phenomenon more technically. So I'm going to give an intuition building example. In particular, we're going to go through this result, which is that optimal hardness of NP and I/O implies optimal one-way functions. Okay? And so the first thing we're going to have to do is talk about how hard NP is. Okay? So P versus NP, I guess, was first stated 52 years ago. And the question is whether if you have an NP algorithm for something, do you have a polynomial time algorithm for something? You could ask, like, what's the best thing we know right now? So what's the best thing we know right now? If you have an NP algorithm, and it uses W bits of non-determinism and runs in time t, then the best algorithm we have for it deterministically is that you run in like 2 to the W times poly t. I don't really care about this poly t, so right. And as far as we know, this is the best we have. In fact, it's kind of interesting, like, so my advisor is Ryan Williams, and like, I don't know, I guess one of the results he's famous for is like this NX versus ACC0 paper, and the way he got there, at least before he had that paper, was he was trying to beat this algorithm. And it turns out if you beat this algorithm, if you shave off a super polynomial term here, then you actually prove NX was not in p-poly, which is like embarrassingly weak compared to anything we've talked about today as an assumption, but is like a long-standing open problem in complexity theory. So like refuting this is also kind of interesting, just as an aside. And like if you remember the Cook-Levin theorem, like it's like really fine-grained in the sense that like circuit SAT, and in this talk, whenever we talk about SAT, we talk about circuit SAT, kind of completely characterizes this question. So like the question is equivalent to basically saying is 2 to the n times poly s optimal for circuit SAT. Okay, so that's just a review of how hard is NP. And so basically, when we talk about NP being optimally hard, we're going to talk about like, is this the best you can do? And I don't know. Let's do, maybe who thinks that this is that you can do better than this? Super polynomially better than this. Anyone?
Who thinks that?
Yeah, just raise of hand.
That this is indeed optimal?
Yeah, like you can't beat super polynomial and n. I guess let's set s equal to poly n. And then, yeah, does anybody think it? Who thinks that this is optimal? Okay, a few brave. Nikon, you want to weigh in on this? No, you don't want to weigh in this? That's fair enough. That's fair enough. That's fair enough. By the way, Nikon's my roommate of 2 years. So, yeah, great guy. All right, let's get back to the. So what's the theorem for one-way functions? So the precise theorem we want is that if you have sub-exponentially secure I/O, and note that like we're not assuming that we have I/O that's like exponentially secure or optimally secure, and the brute force algorithm is optimal for NP, specifically that like whatever that the corresponding term is necessary, then there exists an optimal one-way function, and that in particular means that like for any t you choose, like the success probability you can get is at most poly t over 2 to the n. Okay, this is the theorem we want to prove. Any questions about the theorem?
So again, of course, you're talking about a family,
Yep.
and you are assuming here SETH.
Yeah, it's even. Well, it's kind of incomparable to SE. Yeah. Yeah.
Just like checking the slash on the left-hand side, it's not like a divide. It's like a and or.
Sorry. It's a divide.
It's a divide.
It's saying like, I'm saying you break the assumption if you beat this by super polynomial.
Okay.
So I'm saying you divide by at most polynomial
Okay.
is what I'm trying to say.
Thanks.
Yeah, it's a little confusing.
Thank you.
Yeah.
Can you use the sub-exponential part to smuggle in some hardness for NP?
As far as I know, sub-exponentially secure I/O only implies sub-exponential hardness of NP. As far as I know, it doesn't imply more than that. So it seems like, yeah, the first thing gets you to sub-exponential hardness, but past that, it seems like you need to know something about NP in order to get something. Oh, and I should point out that this is like necessary for this, because yeah. Okay, great.
On the left, is it non-uniform? Like, are you thinking?
Good. I believe it's whichever you want. Is that right, Alex?
Sorry, what was the question?
It's like, can you make it uniform or non-uniform? I think it's like if you want uniform, you can get.
Yeah,
As long as it's uniform on both sides, then yeah.
quality in some sense inherent to the setting, the modeling? Is there hope to get a tighter result? Because for practitioners,
Oh, the poly you're saying is like bad?
yeah, for practitioners, if you think about concrete security primitives like AES, they want. I don't know how to model it, but is it?
Bro, on the right hand side we get T, not poly T. This T and the T are not the same.
This T and
You
that.
just get
Oh,
T.
you're right. This T and that T are not the same. Yeah, that's true.
Oh, on the right hand side it really does say T. Like order T.
Order T.
Yeah. Okay. Right. So now let me tell you about how to prove this. And when you see how to prove it, you'll also see a little bit more. Maybe the theorem statement will also become more. Good. Oh wow, we're chilling. All right, nice. So we're gonna do a warm up, right? We're not gonna do the full theorem yet. We're gonna do kind of baby version of the theorem that it's gonna be useful for when we prove the theorem. Okay. The baby version is like we're not going to try and construct a one-way function yet. We're going to construct something that will be very useful for constructing a one-way function. We're going to try and get like a fine-grained worst case to average case reduction for search set. Okay, what do I mean by that? I want some distribution D that's like sampleable in polynomial amount of time. The distribution D was going to spit out a circuit in a satisfying assignment. And what I want is that, solving search set on C is exactly as hard as solving a worst case instance. And now to talk about this, I really have to introduce parameters because the circuit has two parameters, n and s. This worst case instance also has parameters n and s. So really what's happening here is like this distribution gets us input a parameter n, input a parameter s. It can spit out a circuit that also has n inputs, but maybe it can blow up the size by polynomial in s. And it needs to be as hard as any other n-input s size thing here. So formally, that's what's happening, but I'm going to hide those parameters after this. Okay, any questions about what I mean by this so far?
So,
Yeah.
why is this not a one-way function already?
Okay. It will be. Will give you a one-way function, but it won't give you an optimal one-way function. Yeah. Okay, good. So I'm going to hide those things. All right, so what would you do, right? Yeah, well, there's a very natural first attempt, which actually just goes based on the literature. There's like a very natural first thing you would do. You want some distribution. You want to come up with a C, and you want it to be like as hard as worst case circuits out. What would you do? So there's this. What you could do is your starting point might be this result by Komogorski et al., which said that if p is not equal to np and you have I/O, you can get one-way functions. And the way that they do that is they talk about obfuscating the all zeros circuit. So in particular, this distribution looks like this. Our W, we're going to sample it to be a uniformly random string. It's going to be the randomness to something else. That's why there's this R here. And then what we're going to do is we're going to sample an obfuscated zero circuit, which is going to be B. And it's just going to be the obfuscation of, this is supposed to be the circuit that always outputs 0. You run with randomness W. Okay? So now we have this obfuscated zero circuit. And now our circuit C, that's supposed to be our hard instance of SAT, is going to take as input X. It's going to plug it in as randomness to the obfuscator, and it's going to check if it equals B. Okay? So this is saying like your hard instance of circuit set is literally find me the randomness that gave me this obfuscated circuit. Okay? Actually, yeah, maybe I should have given this disclaimer. If you haven't seen this result before, it's actually not so important you understand this. What I'm trying to convey is, or what I'm going to convey ultimately is that if you have seen this result, there's a deficiency in this result. And the deficiency is, like this result works really well. It does let you go from basically p not equal to np to one-way functions, but it has some problems in the fine-grained regime. In particular, it's like, what do you want in the end? You want to make sure that the circuit's inputs are like n, and you want to have like a good amount of hardness. It turns out like this thing is like W corresponds to like the randomness complexity of the I/O, and then when you would go through the security argument, you're going to pay in terms of the security of the I/O. So when you try and do this, what actually is going to happen is like you're only going to get this to be a fine-grained reduction if 1, your I/O has perfect randomness complexity, and 2, it has perfect hardness. And so like if our eventual goal is like optimal one-way functions, it seems kind of unfair to assume optimal I/O in the middle. Okay, if that didn't make sense, that's fine. I just want to say that this existing approach does not work in the fine-grained regime all the way to the exponential thing. Okay. But if somebody is confused about that, I'm also happy to answer your question. Okay, so what is our actual attempt? Or, yeah, there's actually a very natural thing. Let's say I hand you, let's say I don't hand you I/O, let's say I hand you VBB, right? You want to come up with the hard instance of SAT. Intuitively, what would you do? Yeah.
Just randomize it.
Random, okay, what does that mean? What is the circuit?
Append some random string to the end or to the input that it takes in W XOR R instead of just W. And then to find the right witness, you have to find a random string.
Oh, okay, good. Yeah. I think you're right, but I think it could be made simpler. So here's what you could do. You could take an obfuscated point function, okay? What does that mean? I'm going to pick W to be a uniformly random string of length n. And now I'm just going to consider the circuit that outputs 1 if and only if x was my random string, or x was W, right? Is this construction clear? It's really simple. It's just literally an obfuscated point function with a random point, okay? And if you're in the VBB setting, it makes sense that this thing should be as hard as like the hardest case of circuit SAT, because if you had a simulator which only had Oracle access to this, it has to query literally every point in order to try and find this guy. And it turns out, like, if you're thinking about why this is better than the last construction, is that now we can set nothing in here forced us to set the security parameter to something. Previously, we had the W was the randomness complexity, which was tied to the security parameter. But now this is just determining the circuit, and we can set lambda freely. So even though we have a sub-exponentially secure I/O, we can set lambda to be sufficiently large so that we can get like really high amounts of security. If that made sense, then great. If that doesn't make sense, then that's fine. Okay. So now what are we going to do? What's our goal? This is our construction. We want to show that this gives us a fine-grained worst case to average case reduction for SAT. So what we need to show is that if you have an average case solver for this distribution, that implies a worst case solver for search SAT. Okay? That's our goal. Everybody clear on our goal? We have our distribution. Now we just need to prove this implication. And we're going to do this, as alluded to earlier, in 2 parts. The first part, we're going to use I/O as kind of a worst case to average case reduction. Second part, we're going to use some complexity theory. And in fact, like the intermediate step here is going to be really natural. It's going to be like this thing, our distribution D here is like an obfuscated point function. What I/O is going to give us in this worst case to average case reduction is a reduction basically that you can think of this as like an average case hard distribution on unique search SAT, which is search SAT where there's exactly one satisfying assignment to your circuit. And we're going to use I/O to show that that gives you a worst case to average case reduction to worst case search unique SAT. And then, kind of nicely, we know from complexity theory, there's this famous theorem called the Valiant-Vazirani theorem, which says solving unique search SAT is actually exactly as hard as solving worst case search SAT without a unique promise. So this is like some classical complexity theory stuff, and nicely, it's fine-grained. So we don't have to worry about this step, so I won't tell you about this step, but I will tell you about how this step works. Okay? What I say makes sense? Any questions? It would be good for me to go over it again, or? Okay, just recap. We want to get this fine-grained worst case to average case reduction for SAT. It's going to be a stepping stone to optimal one-way functions. What we're going to do is the distribution, our circuits, our average case hard distribution is literally just obfuscate a point function. A point function is something that outputs 1 at a uniformly random point. And the way that we're going to show that that works is we're going to show that if you could solve D, then you can solve worst case search unique SAT. And then we know from complexity theory that when you can solve worst case search unique SAT, you can solve search SAT. And the difference between unique SAT and search SAT is just that there could be many satisfying assignments versus one satisfying assignment. Okay, good.
You just need I/O for point functions. I don't know if it makes a difference.
Okay, for this we just need I/O for point functions. When we get to our optimal one-way function construction, we'll need it for PRFs, actually. Although maybe you could do something interesting, I'm not sure. All right, so this is what we want to prove. I want to sketch this proof. You have an average case solver from this distribution D. we want to get a worst case solver for unique search set. Okay? All right. So now I want to give you an algorithm, right? You've handed me a solver for this thing. I want to come up with an algorithm that solves this thing. Anybody have just any really ideas? They can be bad ideas, big ideas, or something. So I have this thing. It solves random satisfiability search set on random point functions. Now I want to be able to solve it on arbitrary unique set instances. So it turns out the approach kind of has two steps. The first step is this idea of re-randomization. So I'm given an arbitrary C. This thing is the only guarantee I'm given about it is it has exactly one satisfying assignment. Somehow I'm going to re-randomize it. Then after I re-randomize it, I'm going to solve the re-randomized instance and somehow unshift. These are going to be the two steps. These are the only two steps in the algorithm. Okay? So what is re-randomization going to look like? Right? I'm given this arbitrary unique set instance. What I'm going to do, of course, is I'm going to I/O something, right? So I have this C. I'm going to come up with a C tilde. What is C tilde going to be? It's going to be an I/O of a random shift of C. In particular, I'm going to sample some Z uniformly at random. This is going to be like a shift. Now I'm going to consider the function, which basically evaluates C on the shift of X with Z. Okay? And as like a little sanity check, hopefully it should be clear that like whatever the satisfying assignment is for C, I have no idea. I'm given C. I don't know where its satisfying assignment is. But now that I've picked Z, I've uniformly at random and shifted by that, wherever it was, it's now at a uniformly random location. Okay? So now the satisfying assignment has moved to a uniformly random location. Now I can run the solver on C tilde. Now, before, I didn't know where the satisfying assignment was, but now the satisfying assignment has moved to a uniformly random spot. And I've I/O'd it. So now it turns out that like the distribution D and the distribution on C tilde, no matter what C was, are actually statistically, or sorry, not statistically, their truth tables are statistically the same. And because I I/O'd the C tilde, now the solver has to work on it. If the solver works on C tilde, then it's going to find the satisfying assignment for C tilde. Well, what is the satisfying assignment for C tilde? Well, it's just X shifted by Z, so I undo the Z. So the key idea here was that because it's a point function, and it really exploits the fact that this is a point function, I was able to like take the satisfying assignment, make it kind of a uniformly random satisfying assignment. If there are many satisfying assignments, I can't statistically make it like a uniformly thing. And because it was statistical, I was able to exploit the I/O guarantees. But yeah, okay, so this is the proof sketch of this. And so just to recap, we wanted this search worst case to average case reduction. We're going to look at obfuscated point functions. I just sketched the proof of this. It's like some mix of like point functions, of shift, obfuscate, and unshift. And then this thing is like a classical complexity theory thing. Okay? Okay, any questions about this? So hopefully this should be, yeah. Clear? All right, so now I want to build my optimal one-way function, okay? What is the construction going to be? I guess I kind of gave it away, but any guesses as what the construction might be? Well, okay, if someone said, hey, give me the hardest possible one-way function you possibly could. I've handed you I/O and handed you an I/O. What would you do? Did someone say something?
I of PRF.
Great, good. I/O of PRF. And in fact, almost all of our constructions are pretty much I/O of PRF. The construction is very simple. What's happening is in the analysis, somehow you reduce it to some worst case complexity problem.
What's simple about it?
Sorry?
What's simple about it?
Well, I mean, it's 5 letters, right? I hold a lot of information.
Are you doing
These
XIO?
Sorry?
Are you doing XIO? And
Oh, yeah. True. Good. Yeah, okay, we're going to want our PRF to be injective, so we make it length quadrupling. Don't really worry about that. Okay, so now I want to show that this is actually an optimal one-way function, right? And so what I need to show is that, like, inverting it means that you can solve search unique set, which we already showed was like as hard as solving a search set. And I want this reduction to be like fine-grained. Okay? And so it's actually just going to go by a hybrid argument, and there's going to be 3 parts of the hybrid argument. Okay? The first thing, hybrid argument, is I want to show, I want to consider kind of like the setup in the one-way function game. So what's the setup in the one-way function game? You pick some input uniformly at random. You could imagine second sampling the one-way function from the distribution. And then you have this output y star, which is the one-way function evaluated at the point. And the goal is to invert, go from y star back to x star. And I want to say, if you could go from y star back to x star, then you could solve search unique set. And the way that I'm going to do it is I'm going to say, this is indistinguishable from something else, which is indistinguishable from something else. But if the inverter worked on this other thing, then we'd win. Okay? So the second hybrid, what I'm going to do, well, I have a PRF. What's the only thing I can do with the PRF? Or what do you always do when there's a PRF in the I/O game? You're going to puncture it. So in particular, what you can show is that I'm still going to sample x star uniformly at random. But now I'm going to sample what I want y star to be uniformly at random. And then I'm going to change the one-way function to have that value hard-coded into it. So now it's going to evaluate the PRF if x is not equal to x star. But if x equals x star, then it's just going to output y star. And you can show by a simple puncturing argument that these two things are indistinguishable. Okay? So now I've just changed the one-way function to hard-code in this x star and y star. And then now I do the last step. So the last step, I use my hard unique sat distribution. What I'm going to do is I'm going to change the way that x star works. I'm going to sample this circuit C from my hard unique sat. This should be unique search set. Now I'm going to sample y star uniformly as random as I did before. But now, instead of having an output y star if x equals x star, I'm going to have an output y star if this circuit is satisfiable. Okay? Remember, what did this distribution do? It was just a uniformly random point function. What were we doing here? We were picking a point uniformly at random and then outputting y star. So these two things are actually the same by I/O functionality. Okay? And this is my hybrid argument. I'm saying, okay, these are like the setup for that one-way function game. It's computationally indistinguishable from sampling from the hard search set distribution, picking the y star, and then choosing the one-way function to have the one-way function output y star at the satisfying point of C. So now the point is, if you could invert on this, which means you can go from y star to x, you can also invert on this, which means you can go from y star to whatever it was satisfied on. So you can solve search set. Search set on C, which we showed previously was as hard as solving search set in the worst case. Okay. My goal here was to give you a flavor of like why it's like complexity theory, like I/O makes like cryptography into complexity theory. If you followed everything in here, great. If you just got hopefully some flavor of it, that's also great. That's what I would like. But this is kind of gonna conclude my illustrative example kind of thing. So if you have any questions about this illustrative example, yeah.
Why do you need to run the quadruple link to make sure that you're not hitting?
Yeah, exactly. Yeah. Oh, yeah.
So here the gen has secret randomness. Any hope to have one-way functions with a public, like unstructured key?
Yeah, that's a good question. I don't know. What do you think, Alex?
Not if you make non-standard assumptions, there's maybe some hope, right? So like if you had an I/O with the and a PRF with the property that an obfuscated PRF like looked like a random string its description, then you'd be okay, right? So like I don't see any approaches beyond that.
But is there any heuristic construction for such an I/O?
Yeah, the evasive people would know better, but I think they had some.
All right,
I don't know about the status of those things. But.
Maybe we can talk about it after, but yeah, that's a nice question. All right, so let me end with the promised 3 different columns, okay? So our paper in 3 columns, it's like you go from a primitive Q to some worst case problem to hopefully some complexity class. And what we saw today was that you could take the one-way function primitive, it kind of mapped to this problem unique search set, it did that by some like point functions and punctured PRF argument. And that kind of corresponds to P not equal to NP. And this was by Valiant-Vazirani. And in fact, this whole line is kind of fine-grained, so if you say that this is optimally hard here, you also get optimal one-way functions here. Okay? You could also try and run this with PRGs. Okay, so for PRGs, what would you guess that this problem pi sub q is? Any guesses? So maybe you'd guess that because one-way functions and PRGs are the same, it should be the same problem. But it turns out that since the one-way function game is like a search problem and the PRG game is a decision problem, this turns out to be like the decision version of unique SAT. And this is also by a similar point function and punctured PRF argument. Now, you want a fine-grained way to go from unique SAT to a complexity class. And you'd maybe guess that this is P not equal to NP again. But there's a problem. Because in the exponential time regime, Valiant-Vazirani, when you get to the fine-grained regime, Valiant-Vazirani actually doesn't work here. Because like here, you could imagine you have a solver for this guy, like a BPP algorithm, where like the success probability was like 1/2 plus 2 to the minus 0.99n. So now I have this BPP solver, right? And I want, for unique SAT, I want to turn it into something for SAT. If you try and run Valiant-Vazirani on that, you're going to run into the difficulty that like distinguishing a coin with 1/2 plus epsilon advantage requires 1 over epsilon squared. When you get that epsilon squared, it's going to kill you. So actually, we take a different route. This actually turns out, at least we showed, like it's implied by like NP not equal to co-NP style assumptions in the fine-grained regime. And the way you get this is by Goldwasser-Sipser, another classical complexity theory result. Although actually it turns out Goldwasser-Sipser doesn't help you anyway, because it also has a quadratic dependence. But but then we figured out that you could actually make that quadratic dependence linear. And actually that's kind of cute. Yeah, if you're interested, I have an extra slide on it. Okay, and then like the story for one-way product functions is kind of similar, except now you go from one-way product functions to like a k-fold version of SAT. And then this actually kind of somewhat surprisingly also corresponds to NP not equal to co-NP. And this actually is kind of our most complicated. So kind of like technically like these things are kind of like the most interesting technical parts of our stuff, even though I didn't talk about them so much. This is actually probably our most involved thing, and kind of interestingly, even though these are two worst case problems that we're kind of doing complexity reductions in between, we use I/O here, which is kind of fun. And then so for other problems that I didn't talk about, like extremely lossy functions, there's like a very natural pi sub q for this that you can show using some techniques that I couldn't find to figure out a short description for. Interestingly, it's not clear what like complexity class this corresponds to, if any complexity class. It kind of smells like SCK, really smells like NISCK, but they seem a little bit different. And you can also get at least halfway for correlation intractable functions, and even quantum advantage via Simon problem. You can get make that work, assuming the worst case hardness of some white box thing. I don't know. I think we covered a lot of technical details, so I don't want to say too much. But if you're interested, you can ask me. I'm most interested in this problem, YFP. Anyone know YFP? YFP is your favorite problem? Yeah, YFP is your favorite problem. This is, at least I heard this joke from Ilya Vokovich, but I liked it. But yeah, I think there's a lot of primitives. We thought about some stuff, but we didn't think about everything. Like, there's lots of stuff we didn't think about, and I think it's really interesting. At least filling out this second column here is really interesting, and hopefully figuring out more things that correspond to classical complexity classes, I think, is nice. But yeah, thank you very much. Oh yeah, just some open questions. Like one thing that we did think a little bit about, I mean not too much about, but like what is the worst case problem for FHE? FHE does have like kind of a different smell than the other things, where it's like not like really a circuit-based thing, so it's not clear what it would correspond to. Another thing I would really like is like obfuscation for evasive functions. Like maybe there is some really powerful complexity assumption that would get you to that, but I don't know. Oh, obfuscation for evasive functions.
Not DBD, just I/O.
Oh, sorry. Yeah, I see what you're saying. Yeah. obfuscation, well, I guess obfuscation for evasive function is okay, let's say IO. But I think they're the same. Because for evasive functions, it's just 0 everywhere. So like, the simulator actually does nothing. It just gives you a 0. Yeah, whatever. Yeah. Oh, yeah.
And the two reductions to NP versus non are definitely not equivalence, right?
Yeah, I think. Well, okay, there's IO in there too for one of them, so that's definitely not an equivalence. The other one I think is also not an equivalence, yeah. Yeah, so it's possible you could get maybe something weaker there. Yeah. Okay, so I guess I have 4 minutes, so I'll give you this little puzzle. Improving Goldwasser-Sipser. Okay, so there's this. It turns out the best way to understand this is like via the coin problem. What is the coin problem? So let's say we have oracle access to some function. It just maps the natural numbers to a bit, 0, 1. Okay? And it's not really important here that this is infinite. It just makes it easier to state the problem. I just want you to have as many queries as you'd like. And the guarantee is that for every x, f of x is sampled IID from Bernoulli P. And P is either going to be 1/2 or 1/2 plus epsilon. And to be clear, that's like there is one P that is the same for every x. And your goal is to determine, based on oracle access to f, which of these two things is the case. Okay? And the question is, how many queries do you need to solve this problem? And classically, you need 1/epsilon² queries. Now, what I want to ask is, if somebody's able to whisper some advice into your ear, how many queries do you need? So the model is like someone hands you some advice, and you want to be able to, if that advice was correct, you'd get the answer. If the advice was like however it is, you never get the answer wrong with like.
Just to be sure, the model is that you can you pay to ask what is the ith coin flip.
Yep, those are queries. Yeah. Yep. And yeah, I guess there are two resources here. One is like the length of how much advice you get, and the second is like the number of queries you make. But yeah, I guess yeah.
In the worst case or average?
In the average case, yeah. In the worst case, I guess like all the things could be wrong or something, yeah.
If you switched it from like a 0, 1 to like a dice, like you have 6, whether you have like a classical 1/epsilon to the 6, or like how does that scale with like more parameters?
Oh, okay. Well, I haven't told you the answer to the question, or maybe you're asking this.
Yeah, that's what I'm you have like 3 options instead of 2. Like
I'm not sure actually. I'm sure someone in the audience knows.
There is a line of work by Guy Rodman and others about proving properties of distributions. Isn't this somehow an instance of that?
Of the dice or of the non-deterministic?
Yeah, like proving the sample complexity required when you have a prover about properties of distributions.
Oh, okay. I'm not sure. Yeah, it might be worth talking about. Okay, but yeah, this is a nice puzzle to think about. I guess I maybe gave you that the answer turns out to be 1/epsilon, so that's a nice puzzle to think about.
What's the advice?
Is how much advice?
With 1/epsilon bits of advice, which is, yeah.
Is that advice?
Yeah, what's the advice?
Oh, come on. Come on. I should say we actually don't have the lower bound. I mean, we had never thought about the lower bound, but yeah.
No, but can you tell which flavor of advice it is?
Come on! Come on, guys! All right, come talk to me afterwards. And, yeah.
Isn't the lower bound, you pretend as if it's the coin is half or plus the epsilon, and then you answer as if it's half, and whoever does whatever it is will never see that. If you ask this, and 1/epsilon will never see the epsilon.
Okay, all right, we can talk about it, yeah. All right, but thanks, guys.